everyone, welcome back to our Deep Learning series. This is AI Academy, and today we're diving deep into one of the most important activation functions in neural networks, the Leaky ReLU. In this video, we'll explore why standard ReLU sometimes fails, how Leaky ReLU saves the day, and I'll show you exactly how to implement it in PyTorch and TensorFlow. Plus, we'll compare it with other activation functions to help you choose the right one for your projects. So, grab your coffee, hit that subscribe button, and let's get started. Before we jump into Leaky ReLU, let's quickly recap why we need activation functions in the first place. Imagine you're building a neural network without any activation functions. What you'd essentially have is just a series of linear transformations, matrix multiplications, and additions. No matter how many layers you stack, this entire network can be simplified into a single linear equation. That means your super deep network is no more powerful than simple linear regression. This is why we can't solve complex problems like the XOR gate or image classification with just linear functions. We need nonlinearity. Activation functions introduce this crucial nonlinearity, allowing our networks to learn complex patterns and relationships in data. Now, ReLU has been the go-to activation function for years. It's simple, fast, and works great in many cases. ReLU outputs the input directly if it's positive, otherwise 0. Simple, right? But ReLU has a serious problem called the dying ReLU problem. Here's what happens. When inputs to a ReLU neuron become negative, the output is 0. And here's the kicker. The gradient is also 0. During backpropagation, these 0 gradients mean no learning happens. The neuron essentially dies. It never activates again, no matter what input you give it. In extreme cases, you might find that 40 to 50% of your neurons are dead. That's like having half your brain shut down during an exam. This leads to reduced model capacity, slower conversions, and sometimes complete training failure. Enter Leaky ReLU, the hero we need. Leaky ReLU is beautifully simple. Instead of outputting 0 for negative inputs, it outputs a small fraction of the input. F of x equals max of alpha x, x, where alpha is typically 0.01. The key difference is the small parameter alpha. For positive inputs, it behaves exactly like ReLU. But for negative inputs, instead of dying completely, it leaks a small gradient. Think of it like this. ReLU is like a strict bouncer who kicks out anyone with negative vibes. Leaky ReLU is like a more understanding bouncer who still lets them in but makes them pay a small cover charge. Let's visualize how Leaky ReLU works. On the positive side, it's identical to ReLU, a straight line with slope 1. But on the negative side, instead of being flat at 0, we have a gentle slope with gradient alpha. Typically, alpha is set to 0.01, giving us a slope of 0.01 for negative values. The derivative is 1 for positive inputs and alpha for negative inputs. This means gradients can always flow, preventing the dying ReLU problem. Different alpha values give different behaviors. Smaller alpha values are more conservative, while larger ones allow more negative activation. Let's see Leaky ReLU in action, solving the dying ReLU problem. During training, even when inputs become negative, Leaky ReLU neurons can still learn because they maintain a small, non-zero gradient. This continuous gradient flow means no dead neurons, better gradient flow, improved learning capacity, and more stable training. In practice, networks with Leaky ReLU often show faster convergence and better final accuracy. In a recent experiment on CIFAR-10, switching from ReLU to Leaky ReLU improved accuracy by 2.3% and reduced training time by 15%. Now, how do we choose the right alpha value? This is crucial for optimal performance. The most common choice is alpha equals 0.01. This gives a nice balance, small enough to preserve the benefits of sparsity, large enough to prevent dying neurons. Let's look at different scenarios. Alpha equals 0.01. Conservative approach. Works well for most cases. Alpha equals zero point 0.1. More aggressive. Better for very deep networks. Alpha equals zero point 0.2 to zero point 0.3. Risk of losing ReLU sparsity benefits. Research shows that values between 0.01 and zero point 0.1 work best in practice. Going above 0.2 often hurts performance because you lose the computational benefits of sparse activations. Some advanced techniques even learn alpha during training. This is called parametric ReLU, or PReLU, where each neuron learns its own optimal alpha value. All right, enough theory. Let's see how to implement Leaky ReLU in popular deep learning frameworks. PyTorch. In PyTorch, it's incredibly simple. The negative slope parameter is our alpha value. Simple as that. TensorFlow, Keras. In TensorFlow and Keras, it's equally straightforward. Here's a complete working example. And that's it. Your network is now using Leaky ReLU and should be more robust to the dying ReLU problem. Let's put Leaky ReLU in perspective by comparing it with other popular activation functions. Here's what we see. ReLU, fast and simple, but suffers from dead neurons. Leaky ReLU solves the dying problem while maintaining speed. PReLU learns optimal alpha, but adds parameters. ELU, smoother, but computationally expensive with that exponential. In terms of practical performance, speed, ReLU approximately Leaky ReLU, much greater than ELU. Memory, ReLU approximately Leaky ReLU, less than PReLU. Robustness, ELU greater than PReLU, greater than Leaky ReLU, greater than ReLU. So when should you use each? Here's my practical advice for when to use Leaky ReLU. Perfect for very deep networks, greater than 50 layers, when you're experiencing dying ReLU problems, GANs and adversarial training, when training stability is crucial. Real-world success stories, resonant architectures often benefit from Leaky ReLU, StyleGAN uses Leaky ReLU throughout, many state-of-the-art image classifiers use it. Pro tips: 1. Start with alpha equals 0.01, adjust if needed. 2. Monitor dead neuron percentage during training. 3. Consider PReLU for very deep networks. 4. Always compare with baseline ReLU on your specific task. Watch out for: don't use alpha greater than 0.3 unless you have a good reason. Be careful in very sparse activation scenarios and monitor computational overhead in mobile deployments. All right, let's wrap this up. Here are the key takeaways. Leaky ReLU solves the dying ReLU problem by allowing small negative activations. Simple formula: f of x equals max of alpha x and x, with alpha typically equal to 0.01. Benefits: better gradient flow, no dead neurons, improved training stability. Easy to implement in PyTorch and TensorFlow. Use it when building deep networks, experiencing training issues, or need robust performance. Remember, there's no universal best activation function. The choice depends on your specific problem, architecture, and requirements. But Leaky ReLU is definitely a solid choice that addresses real problems with standard ReLU. That's a wrap on Leaky ReLU. I hope this deep dive helped you understand when and how to use this powerful activation function. If you found this helpful, smash that like button and subscribe for more deep learning content. I'd love to hear about your experiences with Leaky ReLU in the comments below. Next, we will dive into more activation functions, so make sure you're subscribed to catch that. You can also subscribe my channel for daily AI news updates from across the world. Until next time, keep learning and keep building amazing AI. See you in the next video.